final topic for chapter 20 is noise. And when we say noise here, we don't mean just like noise that you hear in your ears, acoustic noise. We're talking about what we refer to as noise in spectroscopy, meaning fluctuations, random fluctuations that we see in the signal we get from our instrument. And so noise isn't specific to spectroscopy, but it's something we're constantly and commonly dealing with in spectroscopy. And so ultimately our goal in most spectroscopic measurements is we want a high signal, and so that's our absorbance peak or emission peak that we're trying to measure, compared to the noise or the random fluctuations that we see that we can't really tell apart from the actual signal. So as an example, if we look at the figure on the right, at the bottom where there's just a single spectrum that's measured, you see that we see these up and down motions. We're looking for a peak that looks like this, but our signal is very weak. So we can tell there's a peak there, but we can't, with this amount of noise, it's hard to tell exactly how big it is. And there is actually a second peak right here. It becomes clearer as we see above. But at this level of noise, it's really hard to tell if there actually is a second peak there. And so we want the ratio of our signal, in this case, like 14 units versus our noise, 9 units, to be as high as possible. And so that's the figure of merit that we use. The way we tell how we're doing is we take the ratio of our signal to the noise, and that's what we're trying to improve. Now, when we say noise, to give it a more quantitative value rather than just saying random fluctuations, what we do is if we measure something that doesn't have any signal, so just measure a blank, for example, we'll still get a signal from our detector and they'll have some fluctuations in it. If we take the standard deviation of that, we get what the noise level is. And so we can just take a sample of from our spectrometer with no signal in it, take the standard deviation of that set of numbers, that gives us our noise level. And so one way we can get around noise, the most common way that we deal with it is by averaging. And so because noise is random, if we add more and more of it together, it's just as likely to be positive as negative from wherever the true value is. And so as we add more and more of these together, the positives will cancel with the negatives as they average, and we'll get closer and closer to the true value. And so the signal-to-noise ratio will increase proportionally to the square root of n, where n is the number of spectra or whatever you're measuring that you average. And so we can see this effect here. So this the bottom spectrum is only a single spectrum. If we average 4 of them, we can see, even with just 4, we can now pretty clearly see that there's a peak here, and this peak here becomes much clearer. And as we average more and more, our signal-to-noise ratio gets better and better. So here it's 2 times better. When we average 16, it's 4 times better. Average 64, 8 times better. And 256 is 16 times better. Where we just take the square root of the number of averages to get how much better it is. I don't think 16 is right there. Anyway, it's square root of 256, whatever that is. I think that is 16, actually. Anyway, so there's always some sort of practical limit. And by the way, this is what makes FTIR so appealing, is that it's very easy to average something like 256 spectra quite easily with FTIR compared to other types of instruments. And it doesn't take that long because you can acquire spectra fairly quickly. And so there's always some sort of practical limit, though, to how many averages you can do, because there are long-term changes in the instrument. The temperature will change. You'll have some sort of electrical change. The pressure in the room will change. And all these things will affect the signal that you get from your detector, which limits how long you can actually do averaging, practically speaking.